Good morning, good afternoon. I would like to welcome you to the second Tech Talk organized by SGInnovate and Infineon Technologies. Today, we would like to discuss about the prospects and challenges of quantum computing. My name is Julia Binder and I'm moderating today's Tech Talk. I'm a director for strategy, mergers and acquisitions at Infineon Technologies and managing the German quantum computing industry consortium called QTech. For some years now, second-generation quantum technologies have been arousing increasingly strong interest in business, politics, and society. In addition to the fascinating and stunning properties of the quantum world, it's above all the technical progress made in the recent years that impressive, making the widespread use of quantum technologies seem tangible. In this context, the postulated demonstration of the quantum supremacy by Google in 2019 has attracted particular high attention worldwide. However, the problem solved was purely academic, still without practical benefits, and whether the actual quantum supremacy is there is still a scientific dispute. Nevertheless, the current achievements in quantum computing development are remarkable. Many technological approaches are continuously reporting significant progress. And internationally, there are also many noteworthy industry initiatives dedicated to the advancement of quantum technologies. Quantum computing is certainly the most discussed second-generation quantum technology area, and many experts believe it has disruptive potential, and thus the greatest economic benefit of all quantum technologies. Quantum computing is a new type of computing approach that differs fundamentally from all previous computing methods. By using quantum effects, quantum computers can enable applications that are not feasible even with the most modern supercomputers. In this Tech Talk today, we have exciting panelists to discuss the prospects and the challenges of quantum computing, involving perspectives from different viewpoints, a corporate, a startup, and academic institutions. So let's start with an introduction about basics of quantum computing. For this, I would like to welcome Sebastian Luber. Sebastian holds a PhD in physics and is a Senior Director for Technology and Innovation at Infineon Technologies. As a spokesperson of the Infineon-wide expert group for the second-generation quantum technology, he represents Infineon in a variety of external bodies and activities. Most recently, he has been appointed advisor on quantum technologies to the German Ministry of Science and was a member of the German government's expert council for a national quantum computing roadmap. Sebastian, the stage is yours.
Yes, hello everybody. Thanks a lot for having me. Thanks a lot for the kind introduction, Julia. And I'm very happy that you like to join me in the journey and the challenge to understand the basics of quantum computing in just 10 minutes. As we just have heard, so quantum computing is part of this often called second generation of quantum technologies, which you can separate in various topics, like, for example, communication, simulation, sensing, and computation. And by making use of the basic principles of the quantum world, we have the promise that we get more powerful computation compared to the classical computation. We get more accurate sensors and a different kind, a more secure communication. So what does quantum computing now promise in detail? Let's have a look at the applications, because in the end, every new technology is only reasonable to be used if you can apply it somewhere, making a difference. And there, especially in the regions where classical computers have challenges, for example, in the simulation of chemical reactions, quantum computers promise to make a difference. And here, to give an example, currently, as everybody knows, we have some challenges regarding energy consumption and energy supplies. And a lot of the worldwide energy consumption is used to create fertilizers. And in order to get better fertilizers, it's very important to have a good way to simulate the chemical reactions there. And that's actually a field where classical computers have huge challenges. And the specific properties of quantum computers here hopefully will enable us to have better simulations of the chemical reactions involved, by that design and create better catalysts, and by that have a far less energy consuming way of making fertilizers. Another aspect where quantum computers are supposed to have a great benefit are all kinds of optimization problems. Here again, classical computers have huge challenges because you have so many different possibilities usually involved. And on classical computing, you have to try them one by one, whereas quantum computers, which I will explain in a minute, have the possibility to look at all possibilities in parallel. And again, currently we have huge challenges with respect to supply chain. And we have to adapt very, very often, and sometimes even in real time, our supply chains to accommodate the challenges around. And here again, quantum computers promise to have better solutions or faster solutions to these challenges, to these optimizations problems, and by that create a benefit to the economy as well as society. So now, what is so different about quantum computing compared to classical computing? And to understand that, what helps is to look at how is a classical computer built and what is the difference. What you need here, as always, is kind of a storage element. You somewhere have to store the data you want to calculate on, you want to use on. And in classical computing, it's a bit, right? On quantum computing, it would be a quantum bit. Then you need a second element, which are gates, in order to calculate, in order to manipulate the data you're using. Without that, you can just store just a memory and not really useful. And now the difference, or what is different in quantum computing compared to classical computing, is that you make use of some very specific effects, which are called superposition and entanglement. These are effects which are relevant usually in the very, very tiny particles in the microscopic world, which is around, which you usually don't see because we are macroscopic objects. But you know them from your daily life, right? Superposition here, for example, in a lake or in the sea, you have waves. And if you have several sources for these waves, you get a very complicated pattern for these waves, for this wave pattern, which can be described by a superposition from single sources. So very complicated pattern, but can be described by a superposition of just a few sources. Now let's translate this into the bits, into the data storage, which you have in computing and in quantum computing. What you know from classical computing is the basic storage element can be either 0 or 1. You don't want them to be something in between or to be both at the same time. For quantum computers, by making use of this quantum effect, you can bring this quantum bit into a state, into a complicated pattern where it still has traces of 0 and 1. It's not really that it is at the same time, but it behaves like that. It behaves like having a part of 0 and a part of 1 at the same time. With the single qubit, it's nothing specific. It's okay, it's interesting, but where it becomes really useful if you combine various qubits together. Why that? Because then the number of states, so the number of information multiplies. So you have kind of an exponential behavior. In a single qubit, you can have parts of 0 and 1, so 2 states at the same time. For 2 qubits, it's already 4 states. For 3 qubits, 8 states. And as you know here, for example, with this history of chess and the rise, it soon becomes a really huge number. And already with 300 qubits, you could code more states into your quantum computer than there are atoms in the universe. Now, the challenge is to make use of all of these states at the same time, because in the end, usually you have a problem, a challenge with a single solution. So it's great if you could somehow throw all of these states at the same time at your problem, but in the end, you want to identify the single solution, so the single state, which is giving you the right answer. And that actually remains a challenge. So this translation, this making use of this power, of this exponential power, and extracting the right information, this is still something where a lot of research is necessary. I want to give you two examples, perhaps a bit more hands-on, where there are already algorithms which make use of this exponential power in the quantum world. And one, if you have a card game and you're looking for a specific card, for example, here, the Ace of Spades, what you typically do is you turn each card one by one around until you find the right card, the right answer. So it's kind of a search algorithm that you're using, and you're doing it one by one. So typically, or in average, you need half of all the cards available if you do it 1,000 times until you find the right card. And the quantum computer now somehow has the possibility with this having access to all of these states, all of these cards at the same time, that it immediately after one cycle or just a few cycles already is able to identify the right answer. So you can compare it to a magician if you already had the chance to visit one. So somehow they always manage to come up with the right card after one attempt. There, it's just a trick, whereas in the quantum computer, it's pure physics which allows you to do that. And one reason why it became very popular, or why a lot of research also has been invested here, is there is, for example, the topic of cryptography, where you use mathematical problems which are very difficult to solve on a classical computer. Typical encryption mechanisms currently rely on the topic of on the challenge to factorize huge numbers, where on classical computing, you have to try one by one whether this is a factor of your huge number or not. A classical computer makes use of this exponential number of states, so kind of tries or attempts to tries with all of these various numbers at the same time to find the right answer. And there's already an algorithm called Shor's algorithm, which is capable of doing that. And what you see here is for, on the x-axis, it's the number of bits used in your encryption scheme. And on the y-axis, the time which is usually necessary on a classical computer and a quantum computer to solve this encryption, to break this encryption. And current encryption is safe because on a classical computer, it takes million to billion years to do that. With this new kind of algorithm and this exponential state, a quantum computer, a powerful quantum computer, would be able to do this in just a few seconds. There are other ways to encrypt, so don't get afraid, don't become afraid. So there are other ways to do encryption, which are also safe on a quantum world. Nevertheless, it shows the power. However, current quantum computers are far away from that. So 2 years ago, Google published this supremacy experiment, as we just have heard from Julia, which now later on some new classical algorithms evolved. So from this initial 10,000 years, a classical computer would need to do the same task. It now reduced to roughly 2 days, I think. And also the task which this quantum computer did is completely useless. It's just a pure academic example. Nevertheless, it has already been the first time that an advantage or a speed up of a quantum computer has been demonstrated. So still a long way to go. Nevertheless, also quite some achievement. And let me conclude now with how Infineon, or what Infineon is doing on that one, on that field of quantum computing. So we have this kind of encryption mechanism also in our company, and we prepare for the future quantum computing age by quantum safe encryption mechanisms. We also want to participate in this emerging market of quantum computing by providing components. And there we have very specific know-how in our company, which we make use, which we leverage on to follow 3 technological approaches, which are ion traps, superconductors, as well as semiconductors. And last but not least, we also have this kind of optimization problems, which I tried to describe in our company, and we are actively looking and applying quantum computers to get here an advantage to a better solution to our challenges. Thank you very much for your attention. I hope I could quickly introduce the power of quantum computing, and I'm very much looking forward to the panel discussion now.
Thanks, Sebastian, for this excellent introduction about quantum computing. In addition to Sebastian, I'm pleased to welcome 3 more quantum computing experts for our panel discussion. We will start the panel with a short presentation of our panelists, introducing themselves, their companies or institutes, and their work. And to the audience, we already had it in the chat. Our panelists look forward to answering your questions. So please ask them via the Q&A tool, and our panelists will answer the questions at the end of the panel discussion. We will start with Manas Mukherjee. He is a principal investigator at the Center for Quantum Technologies at the National University Singapore and director of the National Quantum Fabless Foundry. Manas, would you like to start with your introduction?
Thanks, Julia, and thanks, Sebastian, for the nice introduction. I think not much to say beyond that. What we do is one particular platform, which is called Ion Trap Quantum Computing Platform. And currently our main interest is employing machine learning type of algorithms, but quantum part of that, and to try to solve some, let's say, low-hanging problems, which we can provide some better solution with quantum. That's one part. The other part, as Julia was mentioning, we started recently to consolidate the effort of developing a research foundry for quantum devices. And that's where we use more or less all the resources available in the island, which is quite a number, and try to develop these devices which could be used in the ecosystem. And this is done at A** IMRE. Back to you, Julia.
Thanks, Manas, for your introduction. Now I'm looking forward to the introduction of Luber Singh. Luber is assistant professor at the Indian Institute of Science in the physics department. Luber, stage is yours.
Yeah, thanks, Julia. So thanks for inviting for this panel discussion. So my name is Luber Singh, and I'm a faculty member at the Indian Institute of Science, Bangalore, India. I had an experimental research group, in the area of superconducting qubit devices, and our research interests are, something similar, like Manas said, is to make few qubit quantum processors and try to, implement better gates there and new qubit architectures. So we are not currently in the game of scaling up, number of qubits and making large processors, but try to make better processors at few qubit levels. So since I have this opportunity, I would like to say a few words about the place where I currently work. So a couple of years back, Indian Institute of Science, Bangalore set up a virtual center for the Center of Excellence in Quantum Technology. The center has about 40 faculty members coming from different departments, and it covers a broad range of topics in quantum technology, such as superconducting and photonic quantum processors, quantum communication, cryptography, and quantum enhanced machine learning. We are also running a master's degree program in quantum technology with support from Government of India and 4 industry partners. This is to meet the requirements from industry to have trained human resources in the field. The broader vision of the center is to lay solid foundation for quantum technology in India and to promote international collaborative research. Yeah, so back to you, Julia.
Thank you, Luber. And also welcome to Ewan Munro. Ewan is CTO and founder of Anthropica Labs, And Ewan, we are looking forward to your introduction.
Yeah, thank you, Julia, and hi, everyone. It's a pleasure to be here. So I'm Ewan Munro, and I'm the CTO and co-founder of Entropica Labs. We're a Singapore-based quantum computing startup. By background, I'm a physicist. I did a PhD here in Singapore at the Center for Quantum Technologies. And about 4 years ago, I co-founded Entropica Labs. And our focus is really on designing algorithms and software for quantum computation, and principally with a heavy focus on quantum optimization. We work with customers and quantum hardware companies, and we spend a lot of time thinking about the viability of different potential use cases for quantum computers, and how to benchmark these devices, how to identify promising applications, and actually how to run them on real quantum computers. So I'm happy to be here, and I'm looking forward to the discussion.
Thank you, Ewan. So let's start with our actual panel discussion. And once again, to the audience, please use the Q&A tool if you would like to have any questions to our panelists. I would direct the first question to Sebastian. Sebastian, where do you see the biggest social and also the biggest economic potential of quantum computers? And why are, for example, automotive, pharmaceutical, chemical, or also insurance companies are interested in quantum computing?
Thanks a lot for the question. It was surprising for me when I started to deal with the quantum technologies, because to learn that there are still so many challenges, or there are still not so many, but there are still a few challenges where classical computers are really struggling, because you have so much success, so many advances of classical computing. But indeed, as I tried to point out, there's still a lot of problems where you just the classical approach is just trying each possibility, and by that you get very soon a very huge number of possibilities, and then you fail to get accurate or fast solutions. And interestingly, it's really the case in this kind of chemical simulations. So also speaking to representatives which we have in this QTech and this consortium which you mentioned, from chemical companies, they said that very, very often it's just really trial and error what they're doing. So it's not really design. So especially in this heterocatalyst, it's not design, but you just try to modify what you have in order to get the properties you want. And the basic system is a quantum system, right? So this chemical reaction, it follows quantum laws. So it's natural, which is also the foundation of quantum computing, to use a quantum system in order to simulate that or to calculate that. And for these kind of topics, I think I would expect the fastest and the soonest on-take of quantum computing. Yes. For automotive, it's a similar topic. When you have increasing traffic and you want to kind of control that or to steer that, again, it's a very huge optimization problem, and their quantum computers could help, and apparently in the financial world as well. So I think there are a lot of possibilities where this, in the end, is just a tool, could help to solve these problems, and it's an additional tool, a new tool, which can make things which other tools you already have are not able to do.
Thanks, Sebastian, for this explanation. Very insightful. I would also be interested in which time scale or do you expect to see this first benefits? Maybe you can answer this question.
Yeah, I don't expect there to be significant industry applications or use cases in the next 3 to 5 years. I think that the hardware is still progressing, and it needs the time to mature to be able to actually tackle the problems that people want to address with quantum computers. Now, some hardware companies are suggesting that within about 5 years, they might have a device which could potentially tackle some industry relevant problems, but others are maybe being a bit more conservative in their promises. So So I think that we have to keep our eyes on the development of the hardware there. That's definitely what's going to be the key to everything. But one thing we should bear in mind is that the timescale to different applications may not be the same. So it's not like, one day we have quantum advantage for one application, therefore the next day quantum advantage follows for another application. I think that there will be maybe a time lag between finding quantum advantage for maybe a problem in chemistry to finding one which is more in kind of supply chain or optimization, because chemistry is, as Sebastian said, just fundamentally quantum mechanical. So it might be where you would expect to see advantage from quantum computation first. So I would say that it really depends on the use case. I would also say that there are use cases that we know today probably are not going to deliver quantum advantage. I would say that these problems, which are very time critical, where you need to do kind of real-time computations, real-time optimization of something, I don't know, traffic flow or something like that. I think that these are not the right kinds of use cases for quantum computing, even potentially in the longer term, but definitely in the shorter term. I think the resources needed to do a computation at that speed is something that we're better off sticking with our classical technologies for. But maybe I can just say one more thing. I think that the most interesting thing in quantum computing is maybe what we don't know yet, like the applications that will come further down the line around the whole kind of quantum economy itself, where you have quantum computation in tandem with quantum sensing and quantum communication and all of this this new industry, I guess, that we can say that's emerging will be about processing and exchanging and sending quantum information. And it might be some time before we reach that, but I think that's the real promise of this field. Yeah.
Thank you, Ewan. So both of you, Sebastian and Ewan, you talked about use cases. So I would be interested, especially for people who are not deep into quantum computing yet. So what could be one concrete use case where we see a benefit? Manas, I would be happy to hear your opinion on that.
Well, I don't have an answer, unfortunately. Yeah. So it's just to kind of agree what just now Monroe had said. So but I would think maybe quantum computers in near term are noisy, as we know of, and these are called the NISQ devices. So what we would expect maybe in next 2 to 3 years is probably they will play a role alongside with the classical computers in certain problems like optimization of certain types. Or it could be something like a machine learning type of problem where you use classical computers to do certain things, while you use the quantum computers only to get the loss function, for example, or the energy calculation, right? So these are in general kind of low-hanging fruit in the sense that you don't need a machine which is very, very high fidelity. You can work with a low fidelity machine, but with a larger numbers. Yeah. And the advantage I don't necessarily see in the processing time, but in the energy consumption. I think that was one of the points which Sebastian had in the slide, but did not talk about it. But I think that's a major issue, right? I mean, you know it better than anyone else that the current chips, actually not now, but already 10 years back, you can't use all 4 or 8 cores that you have. Yeah? It will burn it off. Yeah? So that the energy is a big issue. Yeah? So I think there probably maybe like an accelerator, the quantum might come in very near future. Yeah, that's, I think, would be kind of, now exactly where it will come, I would believe there is some penetration in some of these specialized machines like the annealing machines, which might come earlier. Yeah. Then there is also possibility of some types of accelerators based on quantum to solve certain problems which are related to data processing, but not a huge data, but smaller number of data. So I think these are kind of the things which we might see in the near term. Yeah.
Thank you. Also to the panelists in the round, if you would like to comment something else of the other panelists, please feel free to comment even without being named by myself.
Yeah, and so, if I could add something what Manas just said. Like you said, current quantum processors as of today, they are noisy. So the first applications that we are expecting to see there are the ones where algorithm is sort of resilient to noise. Algorithms that are basically solving quantum chemistry problems, they tend to be more resilient to noise. So I think these are the first few test cases, particularly from quantum chemistry, that we would see coming and becoming more accessible to a wider community.
Maybe I can add one more point. Sorry. Oh, sorry.
Sure.
Yeah. I was just going to say, I think that Sebastian briefly touched on a point as well, that maybe quantum computers are indirectly delivering value today. If you think about things like post-quantum cryptography, the fact that quantum computers are becoming more prominent in people's minds, and people are thinking, oh, okay, like our cryptographic protocol is going to be broken anytime soon. I don't think that's the case, but it's really accelerated a drive towards developing things like post-quantum cryptography schemes, and so maybe indirectly, the kind of surge in interest in quantum computing has already had an impact on technology and the way that businesses are operating and thinking about the future.
If I may add, yeah, I like this very much, because I think in general, in order to speed up development, it's always good to have a kind of a positive competition. And now you have some fields where there's a quantum computer coming, which is then also of course triggering additional efforts on the classical side, as we have seen this dispute about the Google results. So the initial classical algorithm should have used 10,000 years, and now they reduced it to 2 days. So there's a lot of development ongoing also on the classical side, which is pushed by the quantum computing side. So yes, I like very much this view.
So Sebastian, if you're already talking, I would have a follow-up question. Since you are working in a big corporate, how should companies today prepare for that future which is coming up with quantum computing? Are there any specific strategic priorities in your opinion? And what should companies do first? What are the challenges you foresee for companies?
Yeah, of course, I think it heavily depends on the business model of the company. But if you have, if you're a chemical company, and this is your major business, kind of to for example, design new catalysts, then you have to deal with these at least potential that this new approach would heavily accelerate your development, and it's quite a different approach compared to the classical ones. I mean, in the end, it's the same problem you want to solve, but these quantum algorithms, or even the hardware, they might still influence for the next years heavily how you approach the problem. So you have to deal with these specific topics of quantum. And so what you have, especially as a big corporate, what you have to bring together is kind of this quantum know-how, this very specific quantum know-how, together with the business know-how, or your know-how of your standard business. So it's kind of interdisciplinary analysis, and then perhaps action which you have to take. And I think this is also how I would approach it, or how we try to approach it at Infineon, that you bring together the experts from the various disciplines in a common team, and then assess, okay, what is the impact, what we are seeing, either being on the application side or also on the provider, on the supplier side. And after having this analysis, then really take action and prepare, because it also takes quite, in my opinion, quite some time to build the knowledge, the competence to really understand on the potential, but also on the approach, how to dig into these topics. But very much looking forward also to, or interested in the opinion of the other panelists, because It's great here to have the representatives from various disciplines, so not only the corporate, but also startups and science.
Yeah, I mean, I can say something here. I mean, we work from the startup side with big enterprises, and I think that one thing to point out at the moment is that we're really kind of in a research phase. We're not really in the situation yet where we're going to put quantum computing into real production in the foreseeable future. So this research phase really consists of, I think, enterprises having to sit down and look at their computational challenges and try to identify what their target use cases might be, understanding for those target use cases what they would like to improve about how they do that today. Is it the speed? Do you need to get the answer faster? Or are you okay with, is the runtime not such a concern for you, but you would just like to have a better answer, or you would like to remove some of the approximations that you're making today and solve a more complex form of the problem? Basically, what's limiting the things today? And can you quantify what the potential impact on the business would be? Because if you have many use cases, you might also want to try to prioritize them in terms of this one. If we could solve this one, it would deliver more revenue, or we would save more money or more efficiency or whatever than this other use case. So yeah, I think there's a process now of a lot of, just looking at use cases one by one and ruling some of. It's a lot easier to rule use cases out at the moment than it is to say this is a definite safe bet use case. So it's more a case of don't focus on this one, focus on this other one because it's maybe more promising. I would say that, taking the ideas like of how you would run a quantum computation, the algorithms, what the resources that would be required to deploy it, and putting that up against the operational constraints, like how quickly do I need to solve this problem? Is it a real-time computation? Well, then probably I just need some fast classical heuristic. Is it an advanced planning problem or some scientific simulation where we run the computation for maybe even weeks, but we just want to get a better answer? And then we go off and build a network of factories or roads or whatever, or we actually design and actually go to fabricate a molecule based on this. Then that's maybe more where we should be thinking about applications. Yep.
Maybe if I may add in here a little bit. So of course it's not from the corporate side, but from the academia side. If I look into the problem array, we definitely know that we have a deficit of talent in the community, because the requirement has suddenly surged up. Yeah, we also feel it in academia because we can't pay enough. So now on our side, we do have a steady stream of students, and we see some of them in front of us, right? And so it is a good thing. But on the other hand, I think we need to be much more scaled up, because suddenly it has a big exponential growth in the field. Now, having said that, one thing is also which I think the corporates need to look into is the number of algorithms that are currently available are handful. There are very few, the real algorithms. Yeah. Therefore, one should actually not tie them up in solving known problems, might even think a little more creative to create new problems, which could be solved that quantum currently don't see. So this is a big opportunity in that respect. Yeah. And I think there is very little going on right now, but I think it is a good time for the corporates also to jump in into that.
Thanks for your answers. Manas, in your introduction, you said you're working on ion traps, but we also heard that there are many other different platforms out there, superconductors, neutral atoms, photons, different qubit styles. Why are there so many different technologies compared to normal CPUs and supercomputers? And which platform do you think will be the most promising for the future?
You're asking me, so of course it's one answer, right? I mean,
so then maybe also the other panelists should answer too, to get a diverse opinion.
Okay, so just to be let's take the broader picture here, right? So for quantum, I think we know right now we are able to separate out individual atoms, photons, or even electrons, separate them out and control them. And this is an enormous effort on humanity itself. Yeah. So that's a big achievement. Now, when you do that, you have n number of atoms and n number of ways you can trap an electron. So therefore, you have n number of platforms. Yeah. So now, of course, I would like to look at the evolution of quantum computer physical platforms. If you look at it, if we were having this chat, let's say in 1999, around 2000, right? Then it's a very nice article in Scientific American, so you can look at it. So it talks about NMR quantum computing would be the size of a coffee cup. Yeah, I'm really quoting that. I mean, more or less, yeah. So, and we know now NMR doesn't exist, and we all agree that it is not the platform that will scale up. Yeah? So these are like kind of things we will go through, I believe, as we progress and try to understand, because it's a very difficult way of how we control these individual particles. It's a very difficult thing in general. However, we are gathered over the years a lot of understanding, and we can say, okay, this might scale up, this may not scale up. This is something which we have understood over the years. And so again, looking at another possibility like topological qubits, it has a lot of promise, but it has been there for a long time. But till now, there is not a single qubit yet. So all is at the moment theoretical. So these are kind of the things that that we, at the research level, we should think very, very carefully and even try out even new things. Because at the research level, we have the luxury to do it and we need to do it. While at the level of, let's say, a company which is building a quantum computer don't have the luxury, because they have chosen a path and they have to make it bigger and bigger and struggle with the problems it has, right? But eventually, we also know that the R&D is not a linear process. So eventually, some of these research that grows on in various different platforms will caught up by some others and make a big jump. And then suddenly what was the scale of 3 to 5 years might become only 2 years. Yeah? So I think that's the kind of ecosystem we're going to see. And what we are also going to see is that we might end up in not just a CPU, we also have GPUs these days. So we will see a combination of these, both classical quantum and maybe even quantum type of platforms. Yeah.
Right, so I can certainly add a few more lines here. So I mean, I totally agree with Manis, the perspective he has given why there are so many qubit platforms. I think as of now, it seems like, you know, the race for scaling is on, right? And people have chosen their favorites. And in that race, I mean, each platform has some pros and cons, right? There are certain advantages, certain disadvantages that are associated with each platform. If you were to make an analogy, for example, with semiconductors, right? In quantum computing, I think we are currently, like, you know, in a time when we have several different types of transistors, and we have not yet identified or discovered the right CMOS, right? So we are in that stage. So once we do that, I think it will become sort of course narrower. To answer your second part, like, you know, which platforms seem most promising? I would certainly say, you know, right now, it seems like superconducting qubits, they have an upper edge, and there's a reason for it. You know, the physical size for these devices is large enough that you can do easily integrate multiple and have a good connectivity between them. This size is also useful in order to minimize the cross coupling that can happen in such devices. Over the time, you know, coherence times for these platforms have, you know, it has increased. And you know, with these artificially engineered devices, it further leaves possibility to discover new qubits. So I think with these factors, you know, these advantages being with the superconducting platform, I think it will remain in the race for some time, unless someone does, you know, really fundamental research to kind of completely change the game.
Thank you for these explanations. So we heard that there's a lot of different research going on. What do you see, or what do you think are the challenges to bring this quantum computing research into commercialization? Maybe Luber, you can start with that, and I'm also happy to have the answers of the others.
Okay, I think there's already, this commercialization is taking place. So one is at the level of quantum computing itself. So like you have various of these cloud-based services where, IBM and Google, they offer cloud-based quantum computing platforms. So that kind of commercialization is already taking place. In addition, I think, a lot of peripheral devices that are, necessary for quantum computers, those are being developed and going out from labs to actual commercialization. So particularly, since I come from that community in superconducting qubits, there is a commercialization that has taken place already.
I mean, since no one else is saying, so maybe I jump in also here. So yes, in terms of commercialization, I think it has to mature a bit. I mean, I guess most important in terms of computing, right? I mean, computing time for these machines. I mean, the machine has to do something useful. So I think we are not at that level yet. However, what is happening right now is training, so which is an important part. So through these, you can actually learn how to use the small algorithms and so on and so forth, right? The other aspect, I think what Vibor has touched upon is very, very important. I mean, when we had this race for the going to moon, we had the toasters made, right? So I guess that's what we would see. A lot of cryoelectronics would be developed during this time. Yeah, it's a natural process. Yeah, we would also see many other things which would be developed along the process of developing quantum computers. So the quantum computer is the end goal, but in between you will see a lot of other technologies coming up.
Perhaps may I add? I think it's a challenge currently that, as you say, so the hardware is not yet at a stage where you can really use it for something which is relevant for the industry or society. It's just training. But as soon as you cross this barrier, then probably you will have a huge uptake and a lot of market going on. Until then, I fully agree. I think one has to be completely open-minded to identify areas which you might haven't had thought at the beginning, but which could then also generate revenue or somehow feed the ecosystem to bridge this time until then you really have these big use cases, which definitely the potential is there. But until then, yes, both on the technological platforms, but on all kind of components or services which are around, definitely, to be completely open-minded to identify things which then generates the revenue to survive for the next years. Fully agree. Yeah.
I would have one last question and then switch to the Q&A, because I see that there are many questions in the Q&A. But Sebastian, as you talked about the ecosystems, bringing the ecosystem forward, I would have the question, what do we need to bring that ecosystem further, and where are opportunities, for example, for collaborations between academia and industry, but also between startup and big corporates? So maybe Ewan, and you can comment that from a startup point of view.
Yeah, I think we got now a very good impression that it's a really fast evolving, fast developing field, and at the same time, it has so many different aspects. And I think for a single company or for even for a single or large research institute, it's impossible to address all of them. So for me, key currently is really partnering, that you bring together competencies from startups, from academia, as well as the use cases, or also the production capability of big corporates, to address various fields and then see which one is evolving faster. And as we have heard, it won't be a linear process. So you will get stuck on one platform, then another one will take over, and then perhaps you make another jump. So yeah, in order to involve the ecosystem, you need to bring the people together to have a good, the right minds, the right competencies, and of course you need funding as well, either from generating revenues, or we also see that governments, and I'm very happy about that, also support this. And I think this will remain necessary for the next years.
Yeah, maybe I can touch on, I mean, I largely agree with what Sebastian said. I think on a point that Manas made earlier was the training and the workforce readiness. So one thing that's, I think, really positive that we've seen is that now you have several universities offering quantum technologies master's programs. So this is really, I think, a nice step forward for this industry and this ecosphere, because it's really going to expand the diversity of ideas and talent that comes into this field. Hopefully it kind of shortens the wisdom might be at the moment that you need a PhD to work in quantum computing, right? But that's not necessarily the case. And I think that having formal training programs at universities that are tailored to this industry will really help deliver a kind of and train a more ready workforce. And by the way, at Entropica, we've had some fantastic interns coming from these university programs coming to work with us. So it's something that we've greatly benefited from. And on investment, of course, that's a big question. Of course, I guess money is always good. We always need money to continue these things. There is this talk of quantum winter and the possibility that in particular private capital might dry up if things move a bit too slowly, especially given that we live in a time where there seems to be some amount of hype around quantum computing. But I think that governments in particular are in this for the long run, and I would hope that the large enterprises as well, who really see through the hype and can understand that there is a promise, and that what we should really focus on is not the hype. We should look through that and focus on the technology progress itself. And even if in 3-4 years we haven't reached a use case yet that we can, actually make deliver value with, the progress is there. So the progress in terms of how we understand what we'll use these devices for, how we'll use them, how we'll program them, and also that the hardware progress is there. And I think as long as that progress is there, then I think the industry can kind of weather a storm. Yeah.
Thanks for that excellent answer. I just opened the Q&A, and I would assume, I think we are not able to answer all the questions, unfortunately, but we will go with the highest rated ones. The first one is, are there significant limitations, for example, in temperature or stability, that might prevent the quantum chips to be used in some hardware application, for example, in smartphones?
So yeah, I mean, I can take it, or I can start it maybe. I guess anyone can jump in. So yeah, right. I mean, it's an excellent question, but one thing one has to understand that quantum computers are not substituting classical computers. They are only to do some specialized computing, which classical computers currently don't have an answer. So not necessarily, I think Ivan was also pointing this out, where there is like very fast calculations needed, or the time is critical. Probably in the near term, quantum computers are not to be on your mobile phone or anything, a laptop or of that size. Yeah, so it would be mostly cloud-based. So your current local processor doesn't matter, right? So even if you access it by your phone, it's fine, because you are accessing some cloud somewhere for your calculation on the quantum computer.
If I might add, I think the big advantage of quantum computers is also the largest challenge. So you have this superposition of states, But if you compare to classical computer, one of the big benefits of digital computing is that you're very immune to any disturbances from the outside. So if you have a small disturbance, it stays at 0, it stays at 1, whereas all of these influences in a quantum computer could complicate you the life extremely. And that's also the reason why you see these cold temperatures or this very specific environment in order to protect your very sensitive quantum computer. And as we are not yet there to make something useful out of that, I also think that it will take even further steps in order then to miniaturize it and to make it mobile. So let's first make it as good to really get this industrial use case and then think about mobilization.
Thanks. So Ewan, there's a special question to you addressed. How hardware agnostic are the algorithms you write? Is there something like an operating system that runs on IBM, Google? Can you rely on having the same gates available on all CPUs?
Mm-hmm. Very good question. Yes. I think hardware agnostic is a term that people use, and I can say what we mean by it, if to the extent that in Tropica we use it. It means that we don't necessarily hedge our bets in all of our development on one particular type of platform. So, we see that different types of processors might be better suited to different types of applications or different types of computations. So for example, superconducting qubits are much faster than ion-trapped qubits in terms of the clock speed, but they typically have a lower fidelity at the moment. So if you want to run a longer kind of high fidelity computation, then maybe ion traps, if you don't have a time limit or a strict time limit, would probably be a better bet if you want to run things more quickly, especially if you're doing something like, if you're doing machine learning or optimization or something like that, you might have to do a lot of hyperparameter tuning to get your algorithms to work best. And that means that you're going to run many circuits. And I think that actually, superconducting qubits might be a better platform for that kind of thing, for, prototyping and developing. To what extent can you write hardware agnostic software? That's a different, maybe a different question. I think today everything is, to squeeze the best performance out of devices, you kind of have to program gate by gate, which can make it hard to construct, hardware agnostic programming libraries. But that's the reality of things today. I think that as time moves on and all devices kind of get better, then it will be much easier to have a kind of truly hardware agnostic programming language, operating system, whatever you want to call it. But today, certainly, when you're trying to squeeze the best out of every available device, it's hard to be hardware agnostic in your programming. Yeah.
Thank you. Unfortunately, we are running out of time. We have so many more interesting questions, and unfortunately, we can't take them anymore, because I would all panelists at least give the chance to say a final word in the last 2 minutes. And I would be interested in what is your wish for the future and your conclusion about quantum computing? Is it reality, hype, or is there much hope with quantum computing coming? So would be really happy to hear the opinion of all of you on that last question.
Yep, perhaps I try to start. So I like very much the vision of Ewan, so to look through the hype, and I think that's exactly my wish as well. So it's not a sprint which we are in. It's really, as some people say, it's a competition with nature. So we somehow have to control very specific properties in nature to make use of them. And it's a huge challenge. It's huge progress, but there still remains a huge challenge ahead. So it's not a sprint, it's a marathon. And nevertheless, I see huge potential for this kind of technology. And therefore, I think it's worth it. But yeah, we have to stay tuned. We have to keep moving, and then I'm very optimistic that sooner or later we will bridge this or cross this barrier and really see very nice applications.
Okay, maybe I go next. Yeah. So yes, I fully agree. So I'm more cautiously optimistic, and I think this is coming, but it's not a matter of whether or not. It's more about when and who does it first. Yeah. So I think with these two, I think from academia side, we try to keep a balance between hype and the reality. Yeah. And that's our job, right? But I believe that there has been tremendous development over the years, and backed on that, it's very, very in near future that we will see something useful.
Yeah. So my take on this is not while there are a lot of prospects in quantum computing, a fully fault tolerant universal quantum computer, that's some distance away in future. In the meanwhile, I think what we should be focusing on, relying that immediate devices are going to be noisy, and develop applications which can work with these noisy processors. Apart from computing, I believe quantum technology in general will have its impact soon before computing, particularly in the domain of sensing and communication. So I think while we should keep our eyes open for these domains and this general interest that's there in the field, I'm hopeful that it will bring more people on the with new ideas on the table. So yeah.
Yeah, so I think I'm very bullish on the idea that quantum computing and quantum technologies will have a tremendous impact. The timescale might be uncertain, but we are talking about technologies based on entirely new laws of physics. I mean, new in the sense that we haven't built technologies based on these yet. So I think that's just a tremendous opportunity that will inevitably lead to a widespread impact across the economy and maybe society at large. I don't know if it will come down to the level of personalized devices with quantum instruments, quantum chips, or something like that in your own your own smartphone. But who knows? I think that the future will involve a lot of quantum information being passed between different people, different organizations, and devices will be needed to do all sorts of information processing there. And I would not rule out that, some point down the line, we do have, some kind of quantum instrument in our smartphones doing something. But we have a lot of technology development and also innovation on the entrepreneurial side to identify what those use cases might be. But maybe more in the near term, I would just love to see one of these exponentials, not near term, but before we get to, quantum devices in our pockets, just an exponential quantum speed up, delivering a new material or a new drug, which, saves lives or improves quality of life. Yeah.
Thank you so much. Thank you to the panelists, and also thank you to the audience. It was a pleasure to moderate this tech talk today about this very exciting new technology, quantum computing, and looking forward to hear a lot more about this technology.
Thank you.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye.
Bye.
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 Bye.